looking at 9.3. This time what we're going to do is find the derivative by a simple process. We call it by rule. And this is going to be, 95% of your work when we're dealing with derivatives. You won't have to just use first principles. All right, so if f of x is equal to a constant multiplied by the variable x to the power of n, then the derivative is found quite easily. All we do is take the power down to the front, so the power comes down. We still have that coefficient of x, and then we take one away from the power. I'll just show you with a quick example now. So looking at b, f of x equals negative 6 multiplied by x to the power of 3. Then the derivative, the power comes down. We multiply by the coefficient of x, so negative 6. And then it's x to the power of what we had originally, take away 1. So it ends up being negative 18x squared. Second dot point here, if f of x is equal to a constant, then the derivative is equal to 0. Now that makes sense because if you think of y equaling 10, for example, then you're going to have a horizontal straight line. And the gradient of that line is going to be 0. So remembering that the derivative just tells us the steepness of the line that we're looking at for any value of x, then that's sensible. Let's look at an example here. We've got the line y equaling 8, so it's just a horizontal line that's flat, 0 gradient. So it makes sense that the derivative is equal to 0. When we're talking about derivatives, if we've got the function f of x, then the derivative is f prime of x. So it's that little dash with the x. If we've got our function in terms of y and x, so here we've got y equaling something, then the derivative is what we call y dx. So change in y over change in x is equal to 0. Also what we see here is if we have f of x equaling an expression with various terms, then to work out its derivative, then we just take the derivative of each term. And we can see that in example C here. So f of x is equal to 3x squared plus 4x plus 7. So f prime of x is going to equal the derivative of that term plus the derivative of this term plus the derivative of that term. So the 2 will come down, multiplied by 3x to the power of 2 take 1, plus, think of, for this 4x here, think of that as having a power of 1. So the power comes down, and then we've got the coefficient of x, which is 4, the variable x, and it's just 1 minus 1 is what that should say there. So 1 minus 1. And we know that 1 minus 1 will be 0, so we'll have x to the power of 0, which is just 1. And then the derivative of the constant 7 will be just 0. So you can see there that we're going to get 6x, and this here will just produce 4, and that will just go away. When we're working out the derivative, it's really important that we get it into this kind of format. So f of x equals something x to the power of something. When it's like that, I can apply this little general rule here and work out the derivative. So this applies for examples like this. So we've got 4 over 3x to the power of 5. What I need to do is manipulate that expression so it's in this format. Firstly, what I'm going to do is take the variable up to the top, because it always needs to be up to the top. At the moment it's x to the power of 5. If at the bottom, if I want to bring it to the top, I just have to change the sign. And I understand that that can be rewritten as 4/3 of x to the power of negative 5. Now calculating its derivative, the power comes down out the front, so negative 5. Got the coefficient still. X to the power of what it was previously, take away 1. So obviously we're going to have x to the power of negative 6 there. And negative 5 times 4/3 gives us negative 20 on 3. You can leave it like that, that'll be fine. But if you wanted to express it with a positive power, take x to the power of negative 6 down to the bottom. And there's your derivative. Alright, so here what we have is an expression that's going to involve a radical symbol, and we need to manipulate it again so it's in that format f of x equals a multiplied by the variable x to the power of n. And we're going to do that using this bit of a rule here. So if we've got the qth root of x to the power of p, then we can rewrite that as being x to the power of p on q. And you'll remember this from when we mucked about with our index laws at the beginning of the year. So f of x equals the square root of x cubed. So the square root is just really saying the second root of x cubed. So I've got that 2 there. That's what you need to assume. And then using this bit of, this rule here, then I can rewrite that as being x to the power 3 on 2. So now it becomes pretty easy working out its derivative. The power comes down. We've got the variable to its original power, take away 1. And so that's 3 on 2, x to the power of a half. And that answer there is quite fine. But if you wanted to get it back into the involving a radical symbol, then it's just going to be the square root of x. So x to the power of a half, we know, is the same thing as the square root of x. So it's 3 on 2 multiplied by the square root of x, which we can also tidy up like this as well. So let's take a look at some examples. For a, we've got y equals the square root of x. So we think of that as being x to the power of a half. And the power comes down. It's x to the power of a half, take away 1. So there's a half. And then if we do that subtraction just with our fractions again, it's that negative. And we can take that down to the bottom and express it as a positive power. So there. So it's 1 over 2 lots of x to the half, which is 1 over 2 to the square root of x. For b, we've got 1 over 3 x to the power of 5. So I realise it's just 1/3 of x to the power of negative 5. And now I can work out its derivative. Power comes down. We've got the 1/3, take away 1 from the power. And then tidying it up and expressing it as a positive power. C, 1 over the third root of x to the power of 4. I know that's 1 over x to the power of 4 in brackets raised to the power of 1/3. So it's 1 over x to the power of 4/3, which I can now take that x, bring it to the top and put it as a negative power. Working out the derivative for this, the power comes down. It's x to the original power, taking away 1. So it's negative 4/3 taking away 3 on 3 will give us negative 7/3. With that negative power, I can take it down to the bottom now and express it as a positive power. I can rearrange it now, so it's going to be x to the power of 7 in brackets 1/3. And then we also understand that that part there can be rewritten as being the third root of x to the power of 7. D, there's a lot of work in this one. We've got our expression here, and I'm just going to manipulate it. So I've got x to the power of something for each of those terms. And that's what I've done here. So the 2x is easy. I've taken the x to the power of negative 3 up to the top and express it as being positive. So it's 5/3 of x to the power of positive 3 plus 1/3 of x to the power of negative a half. So square root, so it's x to the half, and then bring that to the top. So change the power of this, change the sign of the power. Now working out its derivative, just applying that basic rule. I get this expression. I want to express the last one, so it's x to the power of a positive power. So you can see there I brought that to the bottom and split it up, so it's x cubed to the power of a half. And of course, with that half, that's just a square root. So now I've expressed it all with positive powers and radical symbols. It's not necessary to go to all of that length and simplify things, but typically what can happen is that you might be given a multiple choice question, and unless you are able to manipulate it and get into that format, you won't recognize the right answer. Just taking a look at the conditions where we can work out a derivative. If we're trying to work out the derivative for a certain value of x, then it must be continuous around that point. And when we inspect it, we must also be able to draw a unique one-off tangent line. So for here, what we can see, if we're looking at x equaling -1, then it's continuous. And so for -1 here, it's going to be very easy for me to draw on a tangent line with no problems at all. I can estimate where that goes. And therefore, we say that it's differentiable at x equaling -1. For x equaling 2 here, it's discontinuous. Okay, so I can't draw this without taking my pen off the paper. It's discontinuous, so therefore it's not differentiable at x equaling 2. For the third one here, you can see there's that sharp point. So whilst it's continuous, I can draw that and then curve up. If I were to attempt to draw a tangent line, I really wouldn't know how to go about it for x equaling 1. So, I would think that I would draw in, for this curve here, I would draw in something that might look like that, or like that for the tangent line. But then what about, does that really marry up with this section here? No. So wherever you see a sharp point like so, it's not differentiable. Where here we want to see a smooth curve, therefore you can easily put on a tangent line, therefore it's differentiable. All right, problem 3, decide if each of the following is differentiable at the given point, and if possible, work out its derivative. So for A here, we've got f of x equaling this, and we're interested for where x equals 5. So there's my rule. Now notice that if I substitute 5 into the rule, I'll end up with 0 at the top and 0 at the bottom, and therefore it's undefined. So there's a point of discontinuity at x equals 5. So because it's not continuous at x equaling 5, the derivative is, the function is not differentiable at x equals 5 either. So remember, it needs to be continuous and there can't be a sharp section. B. We've got 1 over x squared for x equaling 1. So this is going to be a truncus. The basic shape is going to be a truncus with a asymptote at x equaling 0. So g of 1 equals 1 over 1 squared, which equals 1. So g of x is defined for x equaling 1. So therefore we know it's continuous at x equaling 1, and the truncus has an asymptote at x equals 0, not at x equals 1. So we know that basic shape is curved, like so. Now at x equals 1, there's no sharp point in that either, so it's continuous and there's no sharp point. Therefore, we know that it's differentiable at that point. Let's work out its derivative. G of x equals 1 over x squared. So we can rewrite that as being x to the power of -2. Now the derivative, the power comes down, so -2. X, take away 1 from the power. And then I can rewrite it so that it's got a positive power, so it's -2 over x cubed. And then we need to substitute 1 in, because that's the point that we're trying to work out what the derivative is equal to, and we'll produce -2. So what have we just found out? For our rule, 1 over x squared, the steepness of the curve at x equaling 1 is -2. All right, so using CAS to work out the slope of the curve for any value of x, or just derivatives in general, isn't too difficult. Yeah, a bit different for the way I handle it, but I'll give you the same answer. All right, so here's my function. I'm in calculator mode, obviously. First thing I'm going to do is define the function. So menu, actions, define. F of x is going to equal 5x to the power of 4. All right, and therefore it's defined. Yeah, how do I work out the derivative of f of x? I go menu, and calculus derivative. It'll bring up that template. I need to tell the calculator what variable I'm doing the derivative with respect to. So I just need to put in an x here, and it's always going to be an x, or one variable. It'll be one variable for sure for you for your 11 methods, but it is possible to have multiple variables, but I won't complicate things with that at this stage. All right, so what is it that we want to work the derivative of? F of x. It's bolded, therefore you know it's defined, and there's the rule. Now we can also evaluate for a certain value of x. So let's copy that expression. And now if I go given that x is equal to, so given that x is equal to 2, it'll give me the answer I'm looking for. And there you go, you get your 160. Please note that we should never do it this way. Menu, calculus, derivative. We want the derivative of f of x, but we want x to equal 2. So let's just go f of 2. And what this will produce is a 0. Because the way that the calculator has done this is it said, okay, here's my rule for f of x. Let's substitute 2 into f of x. And if you did f of 2, you're going to get a constant, 80. So when x equals 2, f of x equals 80. Then what the calculator does, it says, okay, here's the 80. Let's work out the derivative of 80. And of course, the derivative of any constant is 0. So what we need to tell the calculator to do is saying, hey, we've got a function f of x. Let's work out its derivative. And that will be an expression involving x. Then let's make x equal to 2. So the derivative of f of x will produce 20x cubed. Then if we substitute 2 into this rule, we'll produce 160. This second approach, what the calculator is doing is saying, hey, let's sub in 2 into the f of x and produce the 80. Now let's work out the derivative of that constant 80, and of course that'll be 0. So whenever you're trying to work out the slope of a curve, the derivative for any value of x, you must put it in this kind of approach. Very important. So to finish off on problem 4, we just had to do it by hand and then verify it on our CAS. So here in green here, you've got the steps for doing the CAS. And I've given you enough examples, I think, of doing the derivative by rule. This one here for B, you got 2x squared minus 6x plus 1 over x. So just think about breaking it up so everything is divided by x. And you can see we've got 2x squared on x minus 6x on x, 1 on x, and then you can rechange it, work out the derivative for each part. The first example, you've got a quadratic and you've got yourself a linear factor down here. Let's factorize the quadratic, and then you'll look at cancelling, and then you're going to work out the derivative of x plus 3, which is pretty easy.